Hi, everyone. So I'm Katie Hockman, as he said. I'm a software engineer at Google and the Go team in New York City. So I'm a part of the group of engineers who's been working on the Go module proxy and Go checksum database. So I'm here today to talk about some new things that are happening with Go, with package management and authentication, and help you understand how these things work at a little bit more of a tangible level. So the first thing you need to know about me is that I absolutely adore dogs. And being a Go developer, I've decided that I want to create a set of Go packages that help people be better dog owners, because if dogs are happy, then I'm happy. So I create a new repository on GitHub. I call it Puppies, of course. And I start creating Go packages for all the source code that I want to provide to people. I make a package that can algorithmically determine the best dog walking route in your neighborhood. I make another one that can tell you what your dog is thinking based solely on the sound of their bark. And then I make one more that reminds you to buy a new dog toy every week for your dog so it never gets bored. There are a lot of APIs that I have to use, though, to make this work. I need dependencies for storage, for audio processing, and for maps. But I have a few concerns. I'm worried that I'm going to have challenges with non-reproducible builds. I'm relying on a brand new API endpoint for the map service that I'm using, and if people import my package and are using an old version of maps, then my code isn't going to work for them. It's going to break, and I have no way of guaranteeing that their builds will be consistent with mine. The owner of the audio detection package that I'm using might just get fed up with managing it and decide to take it off of GitHub overnight. All of my builds are broken now, and I'm really stuck. Even worse, there's a cat person out there who's trying to do me harm. And they've hacked the origin server that hosts some of the code that I depend on. All of a sudden, I'm receiving the wrong code, and my packages are no longer working reliably. By the time I figure this out, it's probably too late. So there are a few things I might consider here in order to protect myself and the people that depend on my code. Maybe I just decide to have no dependencies at all, and I write everything from scratch, but that's not really realistic. I can't really do that, right? I have to try to reproduce the APIs that I'm using, and that's going to make the quality of my code suffer, so I can't really do that. I could just vendor all of my dependencies, but that's going to inflate the size of my repository, and I'm worried it's going to be hard to maintain and update over time. Or maybe I just decide to do nothing at all. I just put my trust in the state of things as they are today, trust that my dependencies will never disappear, that GitHub will always give me what I'm asking for, but honestly, that's a little more trust than I'm comfortable with. So I do have some options, but none of them solve all of my problems without creating new problems and risks of their own. So let's explore some better solutions that have popped up recently within Go. Modules can help us with our reproducible build problem. Module mirrors can help to eliminate the risk of disappearing dependencies causing us harm. And a checksum database can help to eliminate the risk of getting the wrong code, making sure that every Go developer gets the same code every single time they ask for it. So these three things, modules, module mirrors, and the checksum database, are what I'm going to be talking about. Let's start with modules. A module is a version set of Go packages that are related to one another in some meaningful way. So in this example, I have my repository, katiehockman/puppies. And in this repository, I have a few Go packages. I have package walk, package bark, package toys. They're all related to one another. They share a lot of the same dependencies. So I put all of these packages inside of a single module that can now be versioned together. And a module's version has a major, minor, and patch component that make up its semantic version. So if you wanted to import a package before the existence of modules, you either had to vendor that source code if you wanted a specific commit, or you just had to rely on the latest version of that package at the source, which might change. Now, packages can sit inside of a module that's a version snapshot in time to uniquely identify it for everyone, and the contents of that module version are never allowed to change. Every new commit to this module version, it has to be backwards compatible. For something to be a module, it only needs one thing, and that's a go.mod file sitting at its root. And that Go mod file looks something like this. It specifies the minimum version of all the packages that your module uses. It's the only file you need to look at in order to figure out which direct dependencies a module has. So you can see semantic versions here, like 1.4.1, as well as some pseudo versions like o.o.o with a date and a commit hash, which can be helpful if you either want to depend on a specific commit or if the repository that you're using doesn't have version tags yet. By specifying that your code relies on a module with version 1.4.1 or later, then you guarantee that everyone who imports your package will never be allowed to use a version older than 1.4.1 with your code. That's because the Go command is using something called minimal version selection to build a module, based on the versions specified in a go.mod file. So as a basic example, let's say we have module A and B, both of which my module relies on. Each of these modules rely on on C, but at a different version. So A requires at least version 1.5, and B requires at least version 1.6. C has also published a newer version, 1.7. If my module relies on A and B, the Go command will choose the minimum possible version that satisfies the constraints of A and B's go.mod files when it's doing a build. So in this case, that's going to be version 1.6. This minimal version selection guarantees reproducible builds because the Go command uses the oldest allowed version of each dependency in the module, in the build, instead of the newest one, which may change from day to day. So now we have consistent, reproducible builds that are no longer contingent on the latest commit history of a dependency. One problem down, 2 to go. So we've solved the problem of reproducible builds. Next, let's figure out what we can do if dependencies disappear. So now that we have a version module that's never allowed to change, we have new opportunities for caching and authentication that non-module mode didn't have. And this is where module proxies come in. This is what the flow looks like without a module proxy. It's pretty simple, right? A Go developer runs a Go command, like let's say go get, and the Go command is going to hit the origin server directly every time the package isn't in the user's local cache. By origin server here, we're referring to any place where Go source code is hosted, like GitHub, for example. So go get changes behavior depending on whether or not the Go command is running in module-aware mode or it's running in Go path mode. But proxies are only used in module-aware mode, so that's going to be the behavior that we're going to talk about. GoGet has a lot of jobs, but it has 2 big ones that we want to discuss. It has to go out and get the code that you asked for, but it also has to understand the new dependencies for your module based on the code it just fetched. It has to resolve those dependencies, and it may need to update your go.mod file. But without a proxy, this can become really expensive really quickly, both for latency and for storage costs on your system. The Go command may be forced to pull down the entire source of a transitive dependency, even if it isn't building it right now, just to make a consistent decision about dependency versions during its resolution. So for the dependency resolution, this is what the Go command is fetching, and this is how much of that source it actually needs. Remember that only thing the Go command needs to understand the dependencies of a module is a single go.mod file. So for a 20 megabyte module, it may only need a few kilobyte go.mod file to do this dependency resolution. That's a lot of storage on your system's cache that's going unused. It's a lot of wasted time connecting to an origin and pulling down a large file when it doesn't really need to do that right now. So for those of you who have been using modules for some time without a proxy and wondered, where is this latency coming from? This is it. So going back to our example with the Go command fetching source code, let's put a module proxy into the picture. If you tell the Go command to use a proxy, then rather than reaching out to the origin server directly like before, it will instead ask for things from the proxy. So now, instead of interacting with an origin server that it doesn't have any control over, it can instead interact with a proxy that has an API that is much better suited for its needs. So let's walk through what this interaction with a proxy actually looks like. So I'm working on my puppies module, and decided that I want to import a new package that tells me information about different dog breeds, because that's important. The first thing I'll do is run go get go dog/breeds. So first thing, the go command has to figure out which version of go dog breeds to fetch, since I didn't specify one. So in hopes of finding the most recently tagged version, the go command is going to hit the list endpoint on the proxy. And in this example, that $go proxy is the proxy server that we've set up in our Go environment. It could be any of them. So the proxy is going to give back a list of versions that look something like this, with tagged versions like 0.1.0 and 0.3.0. And the go command is looking for the latest tagged version, and in this case, that's version 0.3.2. So now the go command knows the latest tagged version, so it's going to hit this special endpoint that's new, an info endpoint on the proxy for version 0.3.2 of Go dog breeds. So this info endpoint is going to give some extra metadata about this tag or branch. So this metadata includes the canonical version as well as some commit timestamp information. It's going to use this canonical version that just got back from the proxy going forward. So now it's time for the go command to start understanding and resolving the dependencies of Go dog breeds at version 0.3.2. And it does this by asking for its Go mod file. And the go command is just going to repeat the previous two steps of requesting the info and mod file of each of its transitive dependencies, walking down the tree one dependency at a time. Now that its dependency resolution is done, it has to actually get the source code that you originally asked for. So it's going to do that next with one more call for the zip file, which actually contains the source. And the really interesting thing here is what's starred up here. It's the ability to fetch information about a module's transitive dependencies from a proxy without requiring the entire zip file to do it. The go command is able to just ask for the pieces of information that it needs to do the dependency resolution based on minimal version selection and never look at the rest. At this point, there's one part of the flow that you might be wondering about. What's that info file doing, and why does the go command need it? In this example, we're requesting the info of version 0.3.2, and it's just giving back the same version that we provided. Well, let's see an example where that isn't the case. Let's instead run go get go dog breeds, but append at master to the end of it. This is telling the go command that we want it to explicitly fetch what's currently at the master branch. So we're going to skip that list endpoint entirely. We don't need it. We'll immediately jump into requesting the info for that master branch. In this case, you'll see that the info given back is a little bit different. This time, we got a pseudo version, which is a canonical version at master at the time of the request. Now, once it gets this canonical version back, it can proceed as before, pulling down and resolving dependencies and requesting the zip file for the contents that it needs at the end. So I've been speaking about a proxy in general terms because there is no single proxy out there. Any server that implements the module proxy specification can be used by the go command. And this specification is given by running go help go proxy. And you can see this back here. It has that list endpoint that we were talking about, which gives the known versions of the given module. It has the info endpoint for some JSON metadata, the mod file for the dependency resolution, and the zip file for the source. I started this section off by saying that module mirrors will solve our problem, but then I just started talking about proxies instead. Well, a mirror is just a special type of proxy that caches metadata and source code in its own storage system to reserve to clients. And mirrors are great for a lot of reasons. They can help solve our initial concern of code disappearing from the source. They cache source code in their own storage system, so the risk of a developer pulling down their code from GitHub no longer harms you or applies to you. If it suddenly becomes unavailable at the source, maybe because the server is down or having issues, then you have a mirror that has a copy of the source code that you should be able to salvage. You'll likely see faster downloads and less storage use on your system because the go command is asking for only what it needs and ignoring the rest. Unfortunately, it should be super easy to use a proxy. You shouldn't need to install anything to use it. You don't even have to have Git or Mercurial installed because the proxy is doing that work for you. All your system needs to be able to do is make HTTP requests to it. So now we have builds that are reproducible, and we have more confidence that disappearing dependencies aren't going to be a problem for us. 2 down, 1 to go. Let's talk about how we can be sure that we can trust the source code that the Go command is fetching for you. I said earlier that the checksum database is the solution to our security concerns. But before we jump into the checksum database and how it works, let's see how you can expect things to work without it. Without modules or proxies, the Go command would fetch source code directly from the origin server using HTTPS at head. You could be reasonably confident that this was giving you what you asked for, but it was still possible that the origin server had been hacked, and that was undetectable by the Go command. And since your code was relying at the latest commit, it did nothing to protect you from a package owner suddenly changing their source code out from under you. With the introduction of modules, we also got something called a GoSum file. You've probably seen this when you've been working with modules, and maybe scratched your head wondering, what is it? And what, if anything, am I supposed to do with it? This GoSum file is meant to act as your record for what source code looked like when you downloaded it the first time the Go command saw it on your machine. The Go command can use them in some situations to detect misbehavior by origin servers or proxies that might be giving you different code than you saw earlier. So here's that somewhat confusing looking GoSum file I was talking about, which sits right next to your Go mod file in the root directory of your module. It's basically a list of SHA-256 hashes of your dependencies and the hashes of their Go mod files. And because it's a cryptographic hash, it's essentially impossible to make any changes to the files in a particular version without affecting the hash. You should never really have to touch this file. It's something generated by, updated by, and used by the Go command, but understanding how it is, how it works, and what it is important in order to understand its limitations. And by the way, if you look at a GoSum file in the wild, it's going to be a lot longer than this one. It's going to include a bunch of modules that probably don't even appear in your go.mod file. And that's just because it includes the GoSum lines of everything the Go command has ever fetched for this module, including any transitive dependencies as well, even if they don't show up in your go.mod file. The Go command can use these checksums for one very cool thing in particular, and that's for detecting whether or not the source code that you're trying to download now is different than it was a month ago when you last saw it. And this GoSum file should be checked into your repository because the Go command can use this as a source of truth going forward for anyone who tries to download your dependencies. Once it's checked into your repository, the Go command will check against your module's GoSum file when it fetches code. So let's say we cleared out our module cache and we need to refetch our module's dependencies all over again. It's going to fetch the dependencies mod and zip files, do the hashes, and it may see that the GoSum lines it just generated don't match the ones that was saved in the previous GoSum file. This might mean that the source code is modified. It could mean a proxy or an origin server has been hacked, or a myriad of things. We don't really know, and all we know is that it's different than what we trusted before, and that we absolutely shouldn't be using it. All of this is a definite improvement from having no GoSum file at all, but it has its limits. The downside? It works entirely by trust on first use, and more specifically, your first use. When you add a new dependency to your module that you've never seen before, including when you upgrade to a new version of dependency that you're already using, the Go command fetches the code and creates the GoSum lines on the fly. It doesn't have anything to check against, so it'll just pop them in your GoSum file without any checking. The problem is, those GoSum lines aren't being cross-checked against anyone else's GoSum lines. You're just accepting that whatever code you just downloaded is the right code, and your GoSum file will be your source of truth for that dependency going forward. So this means that your module's GoSum file might be really different than the GoSum file that the Go command just generated for someone else. Perhaps because you requested them a week apart and the code changed, or perhaps because someone's targeting you to give you malicious code. So it's not a perfect, complete solution to our problem. And to add a little extra risk for receiving the wrong code, you may have realized something really important when I started talking about proxies. Who's to say that a proxy is actually going to give you the code that you asked for? What kind of confidence can you have that the proxy isn't intentionally targeting you to serve you something different than everyone else to try to do you harm? If you didn't check in your GoSum file, what happens if the proxy serves you something different when you ask for the same source code a month from now? All of a sudden, our relatively secure direct endpoint has been replaced by a proxy that has every ability to lie to you and isn't really trustworthy on its own. In the best possible scenario, we can imagine a world where the code author tells us what the GoSum lines should be, and we can always validate against that. But with Go code living in so many sites like GitHub and Bitbucket, there is no single place to host code, and that's a great part of the Go ecosystem that we don't want to have to change to fix this problem. So what we can do instead is the next best thing. Let's at least make sure that everyone agrees to use the same GoSum lines when they're adding something to their module's GoSum file. And we're going to do this by creating a global source of GoSum lines called a global checksum database. Once the Go command gets its code from a proxy or an origin server, it can then verify those contents against this global checksum database to make sure that the hashes it's generating match the ones in this. You can imagine a really simple way of doing this. We could just have a database running on a server somewhere that just gives you the GoSum lines that you're asking for on request. We can tell the community that we'll behave and ask that they trust us to always do the right thing and that everything will always be good. But all that really does is take a problem and move it somewhere else. All we would really be doing is creating a different target for attackers to focus on. You could also imagine a scenario where the checksum database is run by those cat people I was worried about before. With a simple database, it would be easy for the checksum database to start targeting us dog people. They could serve checksums for the real code to all the cat people, but serve checksums for a malicious version of that code to the dog people. Auditing an entire database is difficult and it's expensive. It's also really easy for man-in-the-middle attacks to go undetected and manipulated data to go unnoticed. We shouldn't have to trust the checksum database as a source of truth without any means of holding it accountable. We need a solution that won't let the checksum database misbehave and will make targeted attacks detectable by the Go command and by auditors. We're going to do this by storing our GoSum lines inside of what's called a transparent log. It's a tree structure that's built by hashing node pairs together. And this is the same technique used by certificate transparency to protect HTTPS. You may have also heard this called a Merkle tree if you've been spending way too much time with crypto folks, like me. We use this Merkle tree instead of a simple database as our source of truth because Merkle trees are much more trustworthy. Its main advantage is that it's tamper-proof. It has properties that don't allow for misbehavior to go unnoticed. So once you put a record in a log, it can never be modified in any way or deleted. If a single record in the log is changed, then the hashes would no longer line up. It would be immediately detected. So if the Go command can prove that the GoSum lines that it's about to add to your module's GoSum file are in this transparent log and that everything checks out, then it can be very confident that these are the right GoSum lines to add to your module's GoSum file. Remember that our goal is to make sure that everyone is getting the correct module version from a proxy or an origin server every time they ask for it. And from our and the Go command's perspective, correct means the same as it was yesterday and every single day before that for every single person that asks for it. So it's important that we have a data structure that can't be tampered with. This log provides a really reliable way of proving two key things to auditors and the Go command. That a specific record exists in the log through something called an inclusion proof, and that the tree hasn't been tampered with, specifically that a later tree contains an older tree that we already knew about, called a consistency proof. These two proofs together can give the Go command confidence when validating against a set of GoSum lines in this log. And the Go command is going to perform these proofs on the fly before adding any GoSum lines to your module's GoSum file. We know the community will run a few external auditors too. We hope that they will, since those auditors are crucial for this system to work. They should work together to watch and gossip about the state of this tree as it grows to alert on any kind of suspicious behavior. So I'm not going to go into all the cryptography in this presentation, since that's probably a presentation on its own, but let's just talk about a little bit to give you an idea of how it works. And hey, who doesn't love math? I know I do. So let's jump into an inclusion proof. Let's start with what this data structure actually is and how it's built. The foundation of our transparency log is the GoSum lines, indicated by the green boxes in this image. Let's start by assuming that our log currently has 16 records. For example, record 0 is the GoSum lines for Go Open Census IO at version 0.19.2. These are the only GoSum lines for this module version in the log, and the only GoSum lines that the checksum database should ever serve. And this is something that auditors can be in charge of verifying. From here, we can start creating the rest of our tree. We do a SHA-256 hash of each record's GoSum lines and store them as level 0 nodes. Then we hash together pairs of level 0 nodes to create level 1 nodes, hash together pairs of level 1 nodes to create level 2 nodes, and so on, until finally we end up at level 4 in this example with a single hash at the top of the tree, which we're going to call a tree head. So why create these hashes to begin with? It seems like a lot of work. Well, remember those proofs I talked about? They basically boil down to comparing this top-level tree head, or hash, and seeing if it matches up with those you've calculated and those you've seen before. Let's go through an example of an inclusion proof, which only requires a few of these hashes to work. And proving that a set of GoSum lines are included in this tree is how the Go command will verify the source code that we just got back. So let's say we want to verify the GoSum lines of that Go dog breeds at version 0.3.2, which we just fetched from a proxy, which in this example just so happens to be record 9. The first thing we'll do is we'll hit an endpoint on the checksum database called lookup with our module version. And it's going to give us back 3 things. The unique record number that identifies it in the log, in this case 9, the GoSum lines for Go dog breeds at version 0.3.2 that exist in this log, and a tree head that contains this record. To prove that record 9 exists in the tree, we need to form a path from that leaf up to the head and make sure it's consistent with the head that we were given back. So if we walk up level by level in this example, starting at level 0, that would be 9, 4, 2, 1, and then finally at the top, 0, which is the head at level 4. So Go command can create this known 9 at level 0 by just hashing the GoSum lines it was given, but it's going to need some more nodes in order to create the rest of the path to head. So here, in order to calculate the hash at node 4, we need to hash together nodes 8 and 9 at the level below it. Then we can use that newly created hash at node 4 and hash it together with its adjacent node, 5, to create 2, and so on, until we finally have that top level 4 hash. And if this level 4 hash that we just created at the top of the tree is consistent with the tree head that we got back from the lookup endpoint, then we've done our inclusion proof and verified the GoSum lines that we were looking to exist in the checksum database, and we're done. And as this tree grows, you'll get new tree heads. And you should check that these new tree heads are a superset of the old ones. So the Go command does this. It stores the tree heads as they're discovered, doing a consistency proof to verify that the new tree head it just found is consistent with the old tree head that it knew about before, to make sure that the tree hasn't been tampered with over time. Just as something to note, oftentimes the size of the tree isn't going to be a power of 2, but we still want to be able to do our inclusion proofs in that case, and we definitely still can. So in this example, instead of 16 records, we have 13, which are including some temporary nodes, which are marked by X's in this diagram. The only difference is that our path from leaf to head contains some of those temporary nodes that we need to create on the fly. And then we'll just throw them away when we're done with our proof. And that's really all there is to an inclusion proof. In practice, the last thing we need to figure out is how do we get those inner nodes that are circled in blue from the checksum database in order to do our proofs. And the way these inner nodes are stored and served are through something new called a tile. No, not that kind of tile. This kind of tile. Under the hood, the checksum database breaks this tree apart into chunks called tiles. And each tile contains a set of hash nodes that can be used for proofs and accessed by clients. In this example, we've chosen a tile height of 2, meaning that a new tile is created every 2 levels up the tree. And the actual checksum database has chosen a tile height that's bigger than this because the tree is much bigger. So it's chosen a tile height of 8 in practice. So as an example of how the Go command uses tiles, let's again look at our inclusion proof for record 9. We know that one of the nodes that it'll need for its proof is node 3 at level 2, like before. And this node is contained inside of tile 1, 0. So that's what the Go command will ask for. Using tiles has some nice benefits. Tiles are nice for the checksum database server since they're really cache-friendly at the front end. But it's also really nice for you as a client because they only cache the bottom row of each tile and build any necessary intermediary nodes on top of that. So since we've chosen a tile height of 8, this cuts down a lot on your storage costs. So instead of caching the entire tree, the Go command is just going to cache every 8th level of the tree and build any necessary intermediary nodes on top of that on the fly as needed. So now that you've seen some of the math, let's get back to how this works within the context of Go. This tree is made available to the Go command through the checksum database spec, which is what you're seeing here. It uses the lookup and tile endpoints to retrieve the data that we just talked about. There's an additional endpoint here, latest, which serves the latest tree head that the checksum database has created. It's just used by auditors if they want to incrementally verify records based on the increasing sized tree heads that are provided. And a tree head looks something like this. It tells you the size of the tree for this tree head and its hash value. So in this example, the tree size is 11,131. At the bottom is something really important. It's a signature, which contains the name of the checksum database, sum.golang.org, followed by its unique signature of that tree head. The signature is important because it allows auditors to easily put the blame on sum.golang.org if it serves something that it shouldn't have served. So let's get back to our example with the proxy. The last thing we did was we fetched the zip of Go dog breeds at version 032. So before it updates your Go sum file and your Go mod file, it's going to make a hash of that zip and check that this is the same hash that the checksum database has. So it'll start by doing a lookup of that module version. And the checksum database gives it back the record number, 9, the Go sum lines, and a signed tree head, or STH, that contains it. And based on this record number and the records and tiles already cached and verified on your machine by the Go command, it can start hitting the tile endpoint to get the tiles that it needs for its proofs. And once the Go command is done with its proofs, it can update your module's Go mod file and Go sum file with the new Go sum lines, and we're done. So now, instead of every person in the world individually trusting their first download of a module, the first version that the checksum database signs is the only one that will ever be trusted. And this ensures that the source code for a version of a module will be the same for every single person in the world, since there's a single source of checksums to trust that can be verified and audited. And this all works really well, even with just one single checksum database that everyone uses. The community has the means of holding it accountable, and the Go command does proofs on the fly too, verifying that the checksum database is behaving and that it hasn't been tampered with. And this checksum database is what makes untrusted proxies possible. A proxy can't start intentionally or arbitrarily or accidentally start giving you the wrong code because there's an auditable security layer sitting in front of it. If an origin server is hacked, then it will be immediately caught. Even if the author of a module accidentally changes their tags and changes the bits associated with a specific version from one day to the next, that'll be noticed. And what's really nice about this, like proxies, is that you as a developer don't have to do anything to make this work. You don't have to register your code anywhere in particular. You don't have to manage your own private keys or create your own hashes in a secure source. The checksum database creates the one and only hash for that code and stores it in the log forever. And it's important to note that the checksum database doesn't just solve a problem that proxies created. It's actually a much safer experience than even the direct origin connections were, since it better protects you from changing dependencies, targeted attacks, and hacked origins. So now we have the full picture. We have dependencies that are consistent, that won't disappear, and can be trusted by everyone. And fortunately, if these interest you, I have good news. Me and my colleagues on the Go team have built a module mirror and a checksum database that you can start using today. Our module mirror and checksum database are used by default by the Go command starting in 1.13 for modules users. So if you want to start using it today, simply upgrading to use the 1.13 beta is all you have to do. Under the hood, the Go command has a few environment variables that can be configured that you should be aware of. So Go 1.11 module and Go Proxy have been around since Go 1.11, so you may have seen these before. You can set Go 1.11 module to on to enable module mode everywhere, or you can just leave it at auto if you want to. And you can set Go Proxy to a proxy of your choice to get picked up by the Go command when in modules mode. So if you want to use our proxy, you can set it to https proxy.golang.org. So though this Go Proxy environment variable has been around since 1.11, there have been some changes that are happening that are new for Go 1.13. So you can now add a comma-separated list of sources to try, and the Go command will try each of these sources before giving up. The nature of the proxy and the checksum database is that source code has to be available on the public internet so that it can be audited and can be used by everyone. So if you're using private modules, that's fine. You can still disable the proxy and the checksum database for the domains that you want to skip by listing them in the Go private environment variable. And just a special shout out to the open source project that we used for our transparency log. We used Trillion for an implementation of that Merkle tree data structure that I was describing earlier. We relied on their data store to hold the Go sum lines and corresponding hashes that the Go command uses for its proofs. They're awesome. You can check them out at github.com/google/Trillion. So we've talked about proxy.golang.org and sum.golang.org, but there is one more service that the Go team is providing in conjunction with these, and that's a module index. Index.golang.org is just a simple feed of new modules as they're discovered by the proxy. And you can see this feed at index.golang.org/index. We're really excited about the future of modules, providing a better dependency management experience to developers by creating reproducible builds, making sure that disappearing dependencies doesn't cause you any problems, and making sure that the source code you asked for is actually the source code that you got and that everyone got every single time. And I'm personally happy because now I have a set of solutions that can help me build out my module, which will make for happier puppies everywhere. And the Go team plans on fine-tuning these features, and we hope that you're going to try them out and give us feedback when you can. We'd love to hear how the module mirror and checksum database are working for you, and we encourage you to file issues on GitHub as you spot them. The dogs of the world, thank you.